Welcome to the Generative AI Futures. Today we're doing a deep dive into something really fascinating, maybe one of the most significant scientific nods to AI in ages. We're talking about the 2024 Nobel Prize in Physics. And it went to John J. Hopfield and Geoffrey E. Hinton.
Yeah, it was a big one. And kind of surprising to some, right? A physics prize for work that underpins machine learning. But it makes perfect sense when you dig into it. They weren't just building algorithms, they were uncovering the fundamental physical ideas that let machines actually learn.
Exactly. It wasn't about spotting a new particle or mapping the universe. It was about artificial neural networks, the absolute bedrock of modern AI, and how these two pioneers connected them directly to concepts from statistical physics.
That's the heart of it. The Nobel Committee recognized that to get these networks to learn, to store information, find patterns, and just, massive amounts of data, you had to think about them like physical systems.
Systems that follow rules about energy and probability.
Precisely. Rules like seeking the lowest energy state or understanding the probability of different configurations, it was a huge shift in thinking.
So moving beyond just logic gates and code execution.
Yeah, moving towards seeing intelligence, or at least learning, as something involving energy landscapes, probability distributions, the collective behavior of loads of interconnected bits, kind of like particles in a physical material.
Okay, so that's our mission for this deep dive. We want to get past the headlines and really unpack the technical genius in the key papers from the 1980s that built this bridge between physics and AI. We'll look at Hopfield's energy-based memory idea, Hinton's more probabilistic machines, the Boltzmann machines, and of course the algorithm that really changed the game, backpropagation.
Right. If you really want to grasp how today's generative AI ticks, you kind of have to understand this almost thermodynamic way of thinking that started it all, and that journey really kicks off in 1982 with Hopfield.
All right, 1982. Hopfield publishes this paper in the Proceedings of the National Academy of Sciences. And the title itself feels like a statement, doesn't it? Neural networks and physical systems with emergent collective computational abilities.
It really was a statement, a different philosophy entirely. Before that, AI was mostly about writing explicit rules, programming logic step by step. Hopfield comes along and develops the Hopfield network. It's a specific kind of neural net designed to work like associative memory.
Associative memory meaning, like if I give it part of a memory, it finds the whole thing.
Exactly. You give it a fragment, maybe a noisy version, and it recalls the complete stored pattern. And the crucial part, it didn't need explicit rules for how to do that. It learned by setting up its internal connections based on a physical analogy.
And that analogy was the key, wasn't it? He looked at statistical physics, specifically something called a spin glass.
Yes, the spin glass analogy is absolutely central. Think of a magnetic material, but a weird one. The magnetic spins of the atoms, they interact in really complex, sometimes contradictory ways. Physicists call it frustration.
Frustration, because they can't all align perfectly.
Right. Because of these conflicting poles, the material doesn't just settle into one simple state, like all north poles pointing up. Instead, it can settle into lots of different stable, low-energy patterns. Hopfield saw that and thought, that sounds like memory.
So each stable, low-energy state of the spin glass is like a stored memory in the network.
That's the core idea. Instead of neurons being just on-off switches in a circuit, think of them like these interacting spins. The overall pattern of which neurons are firing represents the state of the system, just like the pattern of spins.
Okay, so how does it retrieve the memory if I feed it a distorted pattern?
It does it by automatically seeking the lowest energy state available from that starting point. Just like a ball rolling downhill finds the nearest valley, the network state relaxes into the nearest stored memory pattern.
Computation as relaxation. That's a cool way to put it. It just settles into the answer.
It does. The network's dynamics describe this flow in what we call state space, the space of all possible patterns. And that flow leads towards these stable points, the memories. If you start anywhere in the basin of attraction around a memory, the network gets pulled towards it.
So it corrects errors automatically just by following these energy dynamics?
Pretty much, yeah. You feed in something incomplete or noisy, and the system sort of cleans it up as it settles into the closest matching stored pattern.
Now, the Nobel Committee specifically mentioned emergent collective abilities. That word emergence feels important here, like it is in physics. What does it mean for the Hopfield network?
Emergence is a huge concept. It's when you have simple components interacting locally, just following basic rules with their neighbors. But globally, the whole system shows complex behaviors that weren't explicitly programmed in.
Like
Hmm.
like individual birds in a flock creating those amazing coordinated patterns. No single bird is planning the whole thing.
Perfect analogy. That flocking pattern is emergent. Same idea here. You have simple binary neurons, just 0 or 1, and simple connections between them. But out of those local interactions, boom, you get sophisticated abilities like memory retrieval.
What other emergent abilities did it show?
Well, things like categorization grouping, similar inputs, error correction, as we mentioned, even recognizing familiarity, knowing if an input is close to something it's stored, the system figures this stuff out collectively.
Okay, let's get a bit technical. To make this physics analogy work mathematically, Hopfield needed an energy function, right? Capital E. What does that look like?
Absolutely. The energy function defines that landscape the network navigates. To make it work, Hopfield needed a couple of key things. First, the neurons are binary. Vi is either 0 or 1. Second, and this is really the linchpin, the connections have to be symmetric.
Symmetric meaning the connection strength from neuron I to neuron J, call it tie, has to be the same as the strength from J back to I, TJ.
Exactly. TJ. That symmetry is vital.
And the energy function itself, how's it defined?
It's written as E equals minus 1/2 times the sum over all pairs of neurons I and J of T times Vj.
All right, let's break that down. E equals 12 T Vj. What's the intuition?
Think about two connected neurons I and J. If the connection T is positive, meaning they tend to excite each other, the energy E is lower when V and Vj are the same, both 1 or both 0. The system is happier or more stable when connected neurons that excite each other agree.
And if T's in negative, they inhibit each other.
Then the energy is lower when they have opposite states. The function basically rewards configurations where the neurons respect their connection strengths. The network tries to minimize this E value overall.
And why was that symmetry, T equals TG, so critical for the physics analogy to hold?
Because without it, you lose the guarantee that the energy will always decrease or stay the same when a neuron updates its state. Symmetry ensures that the network's dynamics always lead it downhill on the energy landscape. It guarantees convergence to a stable state, a local minimum of E.
So if the connections weren't symmetric, the network might just, oscillate forever? Never settle down.
Precisely. You could get cycles, endless loops where the energy goes up and down. The symmetry forces the system towards stability. It makes the energy function act like a proper potential function in physics, always driving the system towards a stable equilibrium, which is the memory.
Okay, makes sense. But practically, how much could these networks actually store? Was there a limit?
Oh yeah, definitely a limit. Hopfield showed it could reliably store about 0.15 times n states, where n is the number of neurons. So for, say, 100 neurons, you're looking at maybe 15 patterns.
This sounds modest by today's standards.
It is. But remember, this was 1982. The breakthrough was proving that this kind of collective associative memory based on physical principles was even possible. It opened the door.
And there was another interesting point about robustness, right? It fails gracefully.
Yeah, that's another hallmark of these collective systems. If some connections, some synapses fail, the whole thing doesn't just crash. Performance degrades gradually, softly. It's more like a biological system than a fragile machine where one broken part stops everything. That robustness comes from the distributed nature of the memory.
Okay, so Hopfield networks were a huge step. Computation is energy minimization, emergent memory. But they had a major limitation, didn't they? They were deterministic.
That's the key drawback. They're fantastic for recalling patterns they've already been explicitly shown by finding the nearest energy minimum. But they couldn't really learn the underlying probability distribution of complex data. They couldn't generate truly new examples based on what they'd learned.
They could only retrieve, not create or generalize in a deep way.
Pretty much. They were stuck recalling specific memories. To get towards true learning, learning the subtle statistical structure of the world, and towards generative models, well, you needed to embrace probability. You needed randomness.
Which brings us neatly to Geoffrey Hinton, working with Terry Sichnowski in the mid-'80s, and the Boltzmann machine. This sounds like the next big leap.
It absolutely was. The Boltzmann machine, or BM, was a fundamental shift. It introduced two really critical ideas for handling complexity. One was stochasticity-controlled randomness, and the other was the concept of hidden units.
Okay, let's take stochasticity first. Why deliberately add randomness or noise into a system that's trying to compute something? Seems counterintuitive.
It does, but think about that energy landscape again. Hopfield networks always go downhill. What if the nearest valley isn't the deepest one overall? What if it's just a small local dip?
The system gets stuck in a suboptimal state, a local minimum. You
Yeah.
can't climb out.
Exactly. To really learn the true deep structure of the data, the network needs a way to explore the whole landscape, not just the nearest downhill path. It needs to be able to occasionally go uphill to escape those local traps and find the better, deeper valleys, the global minimum, or something close to it.
And that ability to sometimes go uphill comes from randomness.
Yes, stochasticity. And this is where Hinton and Sadnowski borrowed another powerful idea directly from statistical physics, the Boltzmann distribution.
Okay, the Boltzmann distribution. What's the connection there?
In physics, the Boltzmann distribution describes the probability of a system being in a particular energy state at a certain temperature. Higher energy states are less probable, but not impossible, especially at higher temperatures.
So they built temperature into the network.
Sort of, yeah. They introduced a parameter, T, analogous to temperature. Unlike the Hopfield network, the Boltzmann machine allows state transitions that can increase the energy E with a probability that depends on this temperature T. It uses the rule P is proportional to E to the minus E over T.
So when T is high, even high energy states are possible, allowing exploration.
Right. And when T is low, the system mostly sticks to low energy states, becoming more deterministic, like Hopfield's. This gives you a mechanism for exploration.
It sounds like annealing metal, doesn't it? Heat it up to let the atoms rearrange, then cool it slowly to get a strong, stable structure.
That's the perfect analogy. It's called simulated annealing. You start the Boltzmann machine at a high temperature, letting it bounce around the energy landscape randomly, exploring widely. Then you gradually cool it, lower T, making it more likely to settle into the deep, low-energy states that represent the best fit to the data distribution.
Very clever.
Yeah.
Okay, what about the second big innovation? Hidden units. Why are they so important? We hear about hidden layers all the time in deep learning now.
Hidden units are maybe the most crucial step towards modern deep learning. In a BM, you have visible units. Those are your inputs and outputs clamped by the data. But you also have hidden units, which are never directly controlled by the outside world.
They're internal. They can do their own thing.
Exactly. They are free to organize themselves, to figure out how to represent important features or correlations in the data that aren't obvious just by looking at the inputs and outputs directly. They learn the latent structure.
Latent structure.
Yeah.
Underlying patterns or concepts.
Yes. Hidden units allow the network to build richer, more abstract internal representations. They can capture higher order relationships in the data, dependencies between visible units that aren't just pairwise. This is how the network starts to build a real model of the world it's seeing.
So how does it learn? How do these hidden units figure out what to represent, and how do the connection weights get set? What's the learning algorithm trying to achieve?
The goal is actually quite elegant, conceptually. The network tries to adjust its connection weights, the Tej or Wij values, so that its own internal probability distribution, let's call it P prime, matches the probability distribution of the real-world data, P, as closely as possible.
So P is reality. P prime is the network's internal theory of reality. And learning is making the theory match reality.
You got it. They used an information theoretic measure called the G metric or Kullback-Leibler divergence to quantify the difference, the statistical distance between P prime and P. The learning rule aims to minimize this G value.
Okay, minimizing a global measure like G sounds computationally hard. How do you know how to tweak one specific weight, deep inside the network, to improve the overall match? This feels like that credit assignment problem again.
It is, and the Boltzmann learning rule provides a really remarkable solution, rooted in statistical physics. It turns out you don't need global information to update a local weight. The rule is surprisingly simple. The change you make to a weight is proportional to the difference between two probabilities.
What probabilities?
It's the difference between the probability that neurons I and J are active together under two conditions. First condition, when the visible units are clamped, forced to match the input data. Let's call this average coactivation P bar plus.
Okay, so that's measuring correlations when the network sees reality.
Right, that's the positive phase. Second condition, when the network is running freely, with no input clamped, just generating its own patterns based on its current weights, call this average coactivation P bar minus.
That's the negative phase, representing the network's own internal model.
Exactly. The learning rule is simply change a by an amount proportional to P bar plus minus P bar minus.
Wow. So if two neurons fire together more often when seeing real data than when the network is just dreaming, you increase the connection strength between them.
That's the essence of it. You adjust the weights to make the network's internal correlations, the free-running phase, look more like the real-world correlations, the clamped phase. And the beauty is, calculating this only requires local information, the states of neuron I and neuron J at different times. You're optimizing a global measure, G, using only local signals.
That's really powerful. Did they show this working?
They did. A classic demonstration was the encoder problem. Imagine you have, say, 4 input units and 4 output units, but the only way information can get from input to output is through a narrow bottleneck of, say, just 2 hidden units.
So you have 4 bits of input information potentially,
Yeah.
24 contestant solve patterns, but only 2 bits of capacity in the middle, 22 of Fortuna store states.
Right. The network has to learn, spontaneously, an efficient code. The hidden units need to figure out a compressed way to represent the 16 possible input patterns using only their 4 possible states, so the output units can reconstruct the original input.
It has to invent its own internal language.
Precisely. And the simulations showed Boltzmann machines could do this. The hidden units developed these efficient distributed codes automatically just by following that simple local learning rule to minimize the difference between the clamped and free phases. It proved the network could learn abstract, latent structure.
That's impressive. But there's always a but, isn't there? You mentioned meeting these probabilities, p-bar plus and p-bar minus. How easy are they to measure? Didn't that involve the annealing process?
Yes, that's the practical stumbling block. To get accurate estimates of those probabilities, especially in the free-running phase, the network theoretically needs to reach thermal equilibrium at a given temperature. That means running the simulation for a potentially very long time, letting it settle into its characteristic distribution.
So for every single update to the weights, you might have to run this long, slow simulation process.
Pretty much. While the Boltzmann machine provided this beautiful, thermodynamically grounded theory of learning deep representations, actually training it on large problems was computationally brutal, incredibly slow. It gave us the why and the what of generative learning, but how the practical efficiency was still missing.
Which sets the stage perfectly for the next major breakthrough, right? The efficient training algorithm.
Exactly. And that arrived just a couple of years later in 1986. Again, Geoff Hinton was a key figure, along with David Rumelhart and Ronald Williams. Their paper in Nature was titled Learning Representations by Back-propagating Errors.
Back-propagation. Even people outside AI have probably heard of it. This is the one that really unlocked deep learning, practically speaking.
This was the game changer for training. While Boltzmann machines showed that deep networks could learn representations using probability and energy, backpropagation provided an efficient way to actually train them, especially the layered feed-forward kind.
Okay, so shifting focus slightly here. Backprop works best for feed-forward networks, where information just flows one way, input layer to hidden layers to output layer.
Yes, that's the typical architecture. No cycles like in Hopfield or Boltzmann machines. Information moves strictly forward. And backpropagation solved the credit assignment problem for these networks in a deterministic way, using calculus, not statistics, and annealing.
Let's revisit credit assignment in this context. In a deep feed-forward network, the output layer makes an error. How do you figure out which weight, maybe 3 layers back, was responsible and how to change it?
That's the challenge. That hidden unit isn't directly connected to the final output or the target value. Backpropagation's genius was using the chain rule from calculus to systematically calculate how much a tiny change in any weight anywhere in the network would affect the final output error.
The chain rule, like linking derivatives together.
Exactly. It's a 2-pass process. First, there's the forward pass.
Okay, what happens there?
Yeah, that's just the network doing its job. You feed in an input. Each layer calculates its outputs based on the inputs from the layer below and the current weights. The signal propagates forward layer by layer.
So for unit J, its input xj is the sum of outputs j from the layer below, weighted by the connection strengths what? Like xj equals of xj.
Precisely. And then crucially, the output of unit J, yj, is usually some nonlinear function of that input xj. The classic one used in the 86 paper was the sigmoid function, yj1, 1 plus exj.
Why the nonlinearity? Why not just keep it linear?
Because if everything was linear, stacking multiple layers would be pointless. A deep linear network is mathematically equivalent to just a single linear layer. The nonlinearity is what gives the network its power to learn complex nonlinear relationships in the data.
Okay, so signal goes forward, nonlinearity happens at each step, and you get a final output. Then you compare that output to the desired target output and calculate the error, E.
Right, usually using something like the sum of squared differences between the actual output y and the target dE equals 12y d2.
Now for the magic. the backward pass. How does the error get used?
This is where the chain rule comes in. You start at the output layer, where you know the error directly. You calculate how much the error E changes with respect to the output AJ of each output unit. Then you use the chain rule to figure out how much E changes with respect to the input XJ that caused that output.
Okay, so you know how sensitive the error is to the signals right at the end?
Yes. And then you propagate the sensitivity backward. For a hidden unit in the layer below, you can calculate how much the total error E changes with respect to its output by summing up the contributions it made to the error sensitivities of all the units it connects to in the layer above.
It's like passing messages back down the network. The output layer says, here's how much you messed up, and passes that info back.
That's a great way to think of it. Each layer calculates its own error signal based on the error signals it receives from the layer above and its own activation function's derivative. It then uses that signal to update its incoming weights.
How does it update the weight wedge, connecting unit I to unit J?
The change in that weight is proportional to the output signal Y coming from unit I, what went into the connection, multiplied by the error signal day calculated at unit J, how much that unit contributed to the overall error. So Goolage is proportional to Y day. The D term itself is calculated using the chain rule, incorporating U wedge.
So the weight update depends on the signal that passed through it and the error signal coming back. It's still a local calculation in a sense, but the error signal day contains information propagated from the final output error.
Precisely. It's computational efficient because you calculate these error signals layer by layer, reusing calculations. You don't have to recompute the impact of every single weight on the final error independently, which would be astronomically slow. Backprop finds the gradient the direction of steepest descent on the error surface for all weights efficiently.
And this efficiency is what finally made training deep networks practical. Could it actually learn meaningful representations like the Boltzmann machine aimed to?
Yes, that was a key point in the 86 paper. They showed it could learn internal representations. The famous example involved teaching a network about family relationships.
The isomorphic family trees, English and Italian.
That's the one. They trained the network on facts like Colin has Aunt Christine from an English family tree and similar facts from an equivalent Italian tree. The input was person, relationship, person, and the output was confirming the relationship type.
And the network didn't just memorize the pairs?
No, the amazing thing was what the hidden units learned. They spontaneously developed patterns of activity that represented abstract concepts like generation, branch of the family, things that weren't explicitly given in the input. The network figured out the underlying structure common to both trees.
It learned the isomorphism.
Exactly. And because it learned that abstract structure, it could generalize. If you trained it on some relationships and then tested it on a new one it hadn't seen, even from the other language's tree, it could often infer the correct answer. It showed backprop could build genuine understanding, not just rote memory.
That's powerful. Now, the paper also mentioned practicalities like optimizing the learning process. Plain gradient descent can be slow, right? Just following the steepest slope.
Very slow, yeah. Especially in deep networks where you can have long, narrow valleys in the error landscape. You can oscillate back and forth without making much progress down the valley.
So they suggested using momentum.
Right. Momentum was a key trick, still used today. The idea is that the weight change at the current step doesn't just depend on the current gradient, but also includes a fraction of the previous weight change.
Like giving the update process some inertia.
Exactly. If you've been heading consistently downhill in a certain direction, momentum helps you keep going that way, smoothing out the oscillations and speeding through shallow regions. The update rule becomes something like ETO plus IOT1, where I is the momentum term.
Makes sense. What about the old fear of getting stuck in local minima? Was that still a big worry with backprop?
They addressed it. They acknowledged local minima exist, but their experience suggested that for large networks, it wasn't as big a problem as theoretically feared. Networks rarely got stuck in bad local minima.
Why not?
One intuition they offered was dimensionality. In a high-dimensional weight space, millions of weights, there are many more directions to move. It's much harder to get completely trapped than in a simple 2D landscape. Adding more connections, more parameters, often creates paths around these minima. While not a formal proof, this practical experience was hugely encouraging.
So looking back at these three key developments, Hopfield networks, Boltzmann machines, backpropagation. It really feels like physics provided the conceptual framework, doesn't it?
Absolutely. Hopfield gave us computation as energy minimization, the idea of emergent properties from local interactions, pure physics thinking. Hinton, with Boltzmann machines, brought in statistical physics explicitly, using probability and temperature to model learning and escape local traps.
And both really pushed this idea of computation as a physical system settling into a stable state, whether that's a low-energy memory or a high-probability representation of the data.
Right. They fundamentally reframed how we could think about machine intelligence, not just logic, but dynamics.
If we were to quickly compare Hopfield and Boltzmann machines again, based on this energy landscape idea, what are the core differences for someone to remember?
Okay, main things. Hopfield is deterministic. It must go downhill in energy due to symmetric weights. Its goal is associative memory, retrieving stored patterns reliably. It's guaranteed to find a local minimum.
And Boltzmann?
Boltzmann is stochastic, probabilistic. It uses temperature noise to allow uphill moves, letting it escape local minima to potentially find better, more global solutions. Its goal is to model the underlying probability distribution of the data, making it inherently generative. It uses hidden units to capture complex latent structure.
But the Boltzmann learning rule, needing thermal equilibrium, was slow.
Agonizingly slow for large networks. That's where backpropagation came in. It wasn't directly simulating a physical annealing process. It was a clever deterministic algorithm using calculus gradient descent to efficiently train deep feed-forward networks.
So Boltzmann gave the deep theoretical link to statistical physics and generative modeling, but backprop gave the practical engine that actually allowed the field to scale up.
That's a perfect summary. Backprop made deep learning feasible. We build today's massive models using backprop and its variants, but the foundational ideas, learning representations, navigating an energy probability landscape, trace right back to Hopfield's and Hinton's physics-inspired insights from the 80s.
It's like a scientific relay race. Hopfield starts with energy and memory. Hinton takes the baton with probability and generation. Then Hinton and colleagues deliver the final florent with an efficient training algorithm.
Well put. And that efficiency allowed us to build networks orders of magnitude larger, leading directly to the kind of generative AI we see today.
So this whole journey really underscores that the AI revolution isn't just about clever code, is it? It's deeply rooted in applied physics.
It truly is. Moving from Hopfield's spin glass analogy in '82 to the complex gradient descent optimizing billions of parameters today, it's all underpinned by thinking about computation as a physical, dynamical process.
The legacy to this Nobel Prize, then,
Yeah.
is really cementing that connection, recognizing that machine intelligence, as we currently build it, emerges from systems obeying principles of collective dynamics, energy, and probability.
Right. And it brings to mind something the mathematician John von Neumann predicted way back. He suggested that future systems of logic might look less like traditional formal logic and more like thermodynamics.
Thermodynamic, because it deals with systems with many components, with information and energy.
Exactly. He called thermodynamics the part of theoretical physics which comes nearest to manipulating and measuring information. And this Nobel-winning work really shows his vision coming true, doesn't it? We're seeing intelligence modeled not just as logic gates, but as these complex systems finding stable states, minimizing energy, maximizing probability.
That shift in perspective from pure logic to something more like thermodynamics, that feels like the real core message here.
I think so. It forces us to see these massive AI models, like large language models, in a different light. They're essentially physical systems settling into low-energy configurations within a landscape defined by unimaginable amounts of data.
Which leaves us with a final thought, maybe a provocative one for you, the listener. If these powerful generative models are fundamentally finding the lowest energy state, the most probable configuration, given their training data, what does that minimum energy state actually represent?
Is it objective truth? Or is it the most statistically stable distillation of all the patterns, biases, and knowledge present in the vast human text and data they were trained on? A kind of thermodynamic equilibrium of information, perhaps. Always seeking balance, but reflecting the landscape it was shaped by.
Something to think about. The deep concepts from physics continue to shape what's possible and perhaps what's inherent in the artificial minds we're building. Thank you for joining us on this deep dive into the physics behind generative AI futures.